Water everywhere and not a drop to drink. Humans need fresh water, and getting enough of it is an ever-present challenge. Yet the Earth is covered in water. Over half of the planet is ocean. The problem, of course, is that you cannot drink it because it is too salty. Desalination is the process of removing salts from salty sea and brackish water to produce fresh water. The goal is simple, but the technologies are complicated and energy intensive, and we often power these processes with oil. Ideally, we do not want to burn any more fossil fuels to get this water, and that is why people sometimes want to use nuclear energy to power the whole process. In this video, we're going to look at the economics and engineering behind nuclear desalination. But first, let me thank our sponsors at the Asianometry newsletter. I write a lot of exclusive content for it. This includes profiles on Taiwan startup space and videos I won't release except on the letter. The link is in the video description below. I try to put one out every week, maybe two. Alright, back to the show. Modern desalination plants use one or more of three technologies: multi-stage flash, or MSF, multi-effect distillation, or MED, or reverse osmosis, or RO. Industrial scale plants often combine multiple technologies together. MSF and MED are known as thermal processes. They use heat to evaporate seawater into a pure vapor. The vapor is then condensed back into water. MSF desalination was invented back in the early 1950s. The system consists of a brine heater that first heats up seawater to a vapor. Then the vapor is fed through 10 to 30 chambers where the pressures are rapidly reduced, thus causing rapid evaporation or flashing. MSF is a reliable and easy to operate industrial process that scales, and scale matters a whole lot. You're making water for entire cities here. Because of that, MSF is the most widely used industrial desalination technology. MSF plants are especially common in the coastal deserts of the Middle East. The world's biggest desalination plant is an MSF plant. The Ras Al Khair power and desalination plant in Saudi Arabia generates 1 million cubic meters of water a day. That's 415 Olympic-sized swimming pools a day. The other major thermal process is MED, multi-effect distillation. You have multiple stages, referred to as effects. In one stage, you spray salt water onto steam-filled hot tubes. The heat coming out of the tubes causes the water to evaporate into steam, and that steam then gets fed into the next stage. This heat reuse cycle means that MED is very efficient. Reverse osmosis is a membrane-based methodology. It uses electricity to push salt water through a semi-permeable membrane made of cellulose or nylon. High pressures are then applied to push water through the membranes. The salts get caught in the membrane while the water gets through. Other membrane-based desalination technologies include electrodialysis, which, without pretreatment, is only usable for brackish water and not full-out seawater. Reverse osmosis processes by themselves, so excluding the cost of pre-processing, tends to be more energy efficient. Thermal processes need about 10 to 15 kilowatt-hour per cubic meter of water. RO, by comparison, needs about 5 kilowatt-hours per cubic meter. On the other hand, thermal processes are very scalable, and their operations far more reliable. The water doesn't require pretreatment like with RO. Middle East countries have the energy to burn, literally, and so energy efficiency sadly tends to be a secondary concern. Regardless of the methodology, desalination is an energy-intensive process, and much of that energy demand is today provided by burning fossil fuels. The considerable environmental damage this causes has led people to look to nuclear energy as an alternative. Kazakhstan and Japan were the first two countries to build legit nuclear desalination plants. In 1973, a sodium-cooled reactor, BN-350, on the east coast of the Caspian Sea provided electricity and nuclear heat to a desalination plant. Located just 12 kilometers from its host city, the reactor complemented a traditional coal-fired power plant. Its heat provided the energy for the first stage of an MED desalination system, the one that uses steam-filled heat tubes. The system worked fine for its lifetime with no reports of sodium leakages or abnormal operations. The reactor was shut down twice a year for scheduled maintenance. The desalination system had 85% availability and generated 40,000 cubic meters of water a day until its closure and decommissioning in the late 1990s. In 1978, Japan commissioned a nuclear desalination plant with the Ohi Nuclear Power Station. The multi-stage flash desalination system was capable of generating 1,300 cubic meters of potable water a day. Since then, Japan has added 9 additional nuclear desalination plants. Many of them are still in operation today, despite being embroiled in various safety disputes with no issues or anomalies. Other countries have fired up their own nuclear desalination plants, including Pakistan, India, and China. We will talk about some of these projects in more detail later on. The cost of desalinated water is highly dependent on plant design, type, and location. These circumstances mean that costs vary wildly from plant to plant. It's hard to get you a solid number across all systems. For instance, a reverse osmosis plant pulling up and desalinating brackish water from deep underground ranges around $3 to $5 per cubic meter at low capacity, under 1,000 cubic meters of water a day. But there are modern industrial RO plants in Florida with far more capacity, up to 100,000 cubic meters a day, and at greater cost efficiencies. Their costs are little over 50 cents per cubic meter. Some see a pathway to 200,000 daily cubic meters at that same cost. For that reason, RO has seen faster recent adoption. Out in the Gulf countries where energy is plentiful and they use more scalable thermal desalination technologies, capacities regularly exceed 100,000 cubic meters a day. But again, this varies from plant to plant. Remember, the Saudi Arabia plant does 1 million cubic meters. The single biggest cost is that of the capital being put in. Millions are being spent on these installations, and the investors need to make back their investment. Nuclear energy's capital costs are yet higher because so much money is being spent up front on the cost of the build. But setting that aside, the biggest operating cost is that of the energy. Doubling the cost of oil raises the cost of water by 70%, which, considering oil's volatility, is a big issue. Consumers don't like having to pay double the price for water from one month to the next. Nuclear's operating cost is very stable. Its uranium fuel costs have little impact on water costs. Again, this is very site-specific. But once it starts running, the day-to-day costs won't really change. Most existing nuclear desalination systems co-generate power and water. The system integration depends on the methodology used. For reverse osmosis, you use the generated electricity to power the whole desalination process. This is relatively straightforward. And since reverse osmosis is the most energy efficient process, albeit with caveats, it works well and there is power to spare. For thermal processes, integration is a bit more involved. The reactor generates steam that first goes into a turbine for generating electricity. The steam is then routed away from the turbine and put into a heat exchanger for the purpose of heating salt water. Most existing nuclear power reactors are larger pressurized water reactors, or PWR, with over 1,000 megawatt capacity. But there is no real reason why smaller reactors can't be used, and several countries around the world are investigating that usage. A nuclear plant is rated for about 40 years, longer than a desalination plant's 25 to 30 years. Depending on their material, thermal desalination processing tubes have to be retubed every 10 to 20 years. Reverse osmosis filters and systems also have to be replaced at regular intervals, so the integration design has to take this maintenance cost and human effort into consideration. Of course, the most important thing is safety. How to keep nuclear desalination safe. Meltdown incidents like Chernobyl and Fukushima negatively impact public perceptions of anything nuclear powered. Nuclear power plants cost a lot of money, and having them get shut down due to public safety concerns is a problem. The biggest risk specifically relating to nuclear desalination is the threat of radioactive contamination of the water. This is especially the case for plants that use thermal desalination technologies. The primary concern is tritium, a radioactive isotope of hydrogen produced naturally, and in all reactors, tritium is highly permeable. It diffuses through many physical barriers, cannot be filtered out, and reacts with water to form tritiated water. Tritium's primary health concern is cancer. The determination of regulatory thresholds is controversial and multi-layered. thus often subject to politics, but limits vary from 100 Becquerel per liter in the EU to 30,000 in Finland. But it is widely agreed that drinking tritium is 25,000 times more hazardous than breathing it. Thus, engineers build barriers between the primary reactor coolant, the liquid that is actually going into the reactor, and the seawater brine being desalinated. There should be at least 2 loops and barriers between them, usually the steam generator and a heat exchanger. The key issue would be to prevent leaks in any of the loops from contaminating the brine with radioactive material. For instance, a leak in the steam generator might release gaseous tritium that then permeates into the water later down the cycle. To prevent this, engineers apply and monitor pressure differentials in the circuits. The various pressures keep leaks from spreading, and unusual discrepancies can be flagged as signs of leakage. This works. The experience so far in Japan, the United States, and Kazakhstan finds that nuclear desalination consistently generates water with tritium levels below international and country-mandated regulatory limits. Take the aforementioned BN350 nuclear desalination plant out in Kazakhstan. Their maximum tritium level was 6 Becquerel per liter in its desalinated water. Japanese systems go further, showing merely 0.5 Becquerel per liter in their secondary loops. Both of these numbers rank below the naturally occurring tritium levels found in rainwater in Seattle, 11.1. Desalination and nuclear technologies both have environmental impacts that should be considered. We've already talked a bit about the tritium and radiation issue, as well as the various strategies engineers employ to mitigate it. Other issues are related to the desalination side of operations. Desalination plants need to take in water from the ocean, and that presents a threat to marine and sea life. Fish larvae, eggs, and plankton get swept up by these plants. Examinations have found that up to 10 to 30% of fish embryos are being affected. Obviously, this is not acceptable and has been responsible for desalination plant shutdowns in the past. Engineers attempt to mitigate these with slower volume intake rates, nets, and other barriers. None of these are specific to nuclear desalination, of course, but we should talk about and plan for them. Atmosphere-wise, nuclear desalination looks to be environmentally benign, and whatever issues that do exist tend to be outweighed by significant secondary benefits in that fossil fuels aren't being burned to get this drinking water. Various countries are pursuing nuclear desalination projects. I'm not going to list all of them, but here's a few worth mentioning. A few countries trialing the feasibility of the technology include Argentina and Egypt. Russia has explored adding desalination capacities to their floating nuclear power plants. These are basically repurposed boats, which is pretty cool. South Korea has integrated desalination capacity to their smart reactor, which is a smaller but safer experimental reactor. They've managed to produce some 40,000 cubic meters of water a day using it, but it seems like they aren't really rolling that out right now. And of course, there's China. China has significant water scarcity concerns. They're building a massive billion-dollar water transfer project, so nuclear desalination makes a lot of sense. As of 2020, China has about 115 desalination facilities, mostly for industrial purposes. They've been building a lot of these, but they're all powered by coal. Their first commercial nuclear desalination project was at the Hongyanhe nuclear power plant, generating 10,000 cubic meters a day. Other projects in Ningde and Haiyang have been proposed. Basically, many countries already have nuclear power plants, and a lot of those plants are already located near saltwater sources for cooling purposes, which makes cogeneration attractive. It makes a lot of sense economically. While solar and wind-powered desalination projects are indeed moving forward, nuclear desalination offers reliably high amounts of potable water at a low operating cost, providing, of course, it is done right and safely. Nuclear desalination is capable of water-led growth for societies and economies. It allows for more water-intensive agriculture, it reduces tension and conflicts over limited surface waters, and it keeps fossil fuels from being burnt. We should explore other renewable energies for powering desalination, but for now, the cost-benefit calculations of nuclear desalination are hard to ignore. Alright, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up to the newsletter, and I'll see you guys next time.